Welcome, everyone, to the Fall 2021 week of Martin Gardner Celebration of Mind Talks. I'm your host, Bob Hearn. I'm a G4G board member and the program chair. And I am very happy for our kickoff speaker to introduce Adriana Salerno. She is originally from Venezuela, now is a math professor at Bates College, and is also the newly elected vice president of the Mathematical Association of America. So congratulations there. And I'm very much looking forward to hearing about higher dimensional origami. So Adriana, you are welcome to take it from here.
Awesome. Thank you so much. Very honored to be included in this lineup. I'm actually confused as to why I'm here with all these amazing people. And so I just want you to be sure to check out the other talks. I feel like if you like this talk, great. And if you don't like this talk, it's only getting better from here. So, I mean, even if you like this talk, that can only mean better things later, right? And so I just want to tout my fellow speakers. And again, I'm so grateful to be given the opportunity to talk about higher dimensional origami, although don't get too excited yet. So, origami is this beautiful art. It's been around for a very long time, but it's yielded a ton of insights in many different areas. People use these to figure out how to fold airbags. There have been like space antenna that have been, people use origami to like fold it into a small thing and then it unfolds in space. So there's lots of different applications to origami. And then obviously there's like the artistic side. And so Robert Lang has been doing these amazing constructions with just paper, no cutting, right? Only folding. And one of the things that he's done is sort of systematize how you design the origami. And so you have all these in his website, which I completely recommend. You see things like this, where you have a unfolded version. And so this is actually the unfolded version of this rhino. And so you can see sort of all the folds. But what I want you to look at is once you unfold this origami, basically what you have is a piece of paper with lines, and those lines sometimes intersect. Okay, and so that's going to be an important idea. And I have another sequence of pictures just so that this is a student, a summer research student made this for a talk that she gave. And so I borrowed this from her. And so you essentially start with a sheet of paper and then you start folding, and those folds sort of create these new reference points. And so sometimes you can use that to make a new fold. And then eventually you get this, this beautiful shape. Now, hold on to your seats, because there's actually going to be no more actual origami in this talk. But there is mathematics inspired by origami. And so, so for those of you who wanted to see a 6-dimensional crane, not going to happen today, at least not in my talk. I'm not sure what other people have in store for you. But we can sort of generalize this idea to do mathematics, okay? And so the game that we're going to play is we're going to, instead of looking at a finite piece of paper, we're going to think about 2-dimensional space, sort of this infinite in two directions. And one way to sort of make it more mathy is to think of the complex numbers, or R2 or the Cartesian plane, right? And so in my case, we're going to use complex numbers. So complex numbers are of the forms of A plus BI. And we conceptualize them as, an I is the square root of -1. And so we can conceptualize a complex number as having 2 coordinates. What's nice about this versus the version where we just write down a point by its coordinates is that we actually can do arithmetic with these points. That's very similar to the arithmetic we do with integers and rational numbers. We can add, we can multiply, we can divide, right? And so with points, you don't get that much freedom. And so that's why we like using complex numbers a little bit better, because we have on top of the geometry part, like this is a two-dimensional space, we also have arithmetic. I'm a number theorist by training, so anything that has arithmetic and operations is very much my bag. And so, and we're going to start with some reference points. Okay, so the idea is we have paper, and then we have 2 points that we have just pinned down as being like our starting points. And then we fold by drawing lines through those points, and we only allow certain angles. Okay, and so and then you can define these in many ways, but what's nice about complex numbers is that you can define either an angle or a vector or a few different ways, or just a point in space. And so what I'm going to call an origami construction means the set that you get after you add all possible intersections. And I'm going to show you how this happens in an example, because this is very hard to conceptualize right away. And this is where we get sort of our, Ron Graham is one of the people that we are celebrating this week. And so, and this is a collaboration. This is from a paper from 2012 by Buhler, Butler, Launey, and Graham. And I will say there's also going to be no juggling in this talk, just in case we're hoping that my tribute to Ron Graham was going to include juggling Rubik's cubes. No things like that. But this is a really neat idea, and I think they say in their paper this was inspired by a question that Eric Deveena asked them, and Deveena is one of the speakers this week, so you can see some more of that. And he's going to do actual origami. So there you go. And so this is the setup. Okay, we're starting with some angles, and so the points are a little light here, but we're starting with a point 0 and 1 on the complex plane. And so that's where we're starting with. Okay, that's our initial set. And what we're going to do is a game where we create new points by drawing lines through those points with these prescribed angles. And so these, I wrote these as points in the complex numbers, but you can see this is basically 0 degrees. This is 45 degrees, or pi over 4 radians. And this one is here, right? And so then this is 90 degrees, or pi over 2 radians. Okay, so you can think of these in many different ways. I think of them as complex numbers, but that's not a big deal. This is not quite 95 degrees. So 45 degrees. So let me redraw that. And so we're going to draw, let's make this blue, a line with slope pi over 4 through this point. Okay, and those are the only lines that we're allowed to draw. We can allow horizontal lines, vertical lines, or this diagonal line. And that's it. And we can only start with a point 0 and 1. So you do that to your heart's content. So you see, for example, that if you draw this horizontal line, you don't get any new points. But these two lines intersect in a new point. And that point actually has coordinates 1, 1, or you can say this is the point 1 plus I. And then the only new points you get is if you draw the same like parallel line, but through 1, and you get this new point. And that point is negative I. Okay. And so now what you do, so the game of the origami construction is you add those 2 points. So now you go from here to set 0, 1, minus I, 1 plus I. Okay, and that's my next slide. And so that's, you add those points, and then you play the game again. And you play the game until you get to a point where there are no more points to add. This, at some point you get everything that you could possibly get. Of course, this is an infinite process, right? So be careful with that. But let's do this again. So for example, I can draw a horizontal line through negative I, and then a vertical line through through 1 again, and I get this new point, right? But then I can do this, and I get this new point. That's actually the point I. And I could do this diagonal and get this point. And then what else could I do? Oh yeah, this one. You could have done this, and it goes through here, but it also goes through here, right? And so you get a few more points, and then you put them in the set, and then you play this game again. Okay, and so then you get this set is what I just showed you, and then you keep going and going and going, and here's more, and then you get this. Okay, and at some point you run out of things to add, so you iterate this process forever until you get all of these points. Oh yeah, so okay, some of you know the fancy name for this. These are the Gaussian integers, right? An integer lattice. Okay, and so for those of you who don't know what Gaussian and integers and lattice means, what we're seeing is we're getting this really, I mean, this is as neat as something can get, right? This is a very, very nice organized grid. And yes, it's called the Gaussian integers, but you can see that what you're getting are combinations of this form where A and B are integers. Okay, so this is a really, really nice subset of the complex numbers. And so, yes, these are the Gaussian integers. You know something is important if it has a fancy name. I'm kidding. But yes, the way that you describe these are all the elements in the complex numbers of the form A plus BI, where A and B are integers. Okay, so somehow this origami construction is this iterative process where you start with 2 points, you're only allowed certain angles. You continue this process until you have no new points of these, and this intersection process until you have no new points. And then of course, what a mathematician asks is, well, what can I say about that set of points? Do I always get something nice like this, right? Or do I get something messy? What kinds of properties, both like geometric, topological properties, but also algebraic properties, can I find there? And this is sort of the core of this exploration. And what I'm going to tell you about eventually is sort of like how we have generalized, me and my students have generalized some of these ideas. But first, I'm going to tell you about sort of this process, this iterative process is actually something you can tell a computer to do. And I had these 3 summer research students a few years ago who coded all of these ideas into Maple, and then they tried to see, well, what happens if I run this for a few generations. One of the things that you may have guessed if you've done these types of processes before is that this gets really complicated really quickly. So they weren't able to get it to run very far, but here are some examples. And so this is just Maple output, in case you were wondering. So you get some really, really neat things like this. You get some messy things like this. And so this is a mess. And then you zoom in and you still get kind of a mess, right? Another mess and a little bit more organized mess. And so, this is the moment where I ask you, what do you notice and what do you wonder about these sets? The whole point of making examples and having a computer do examples is that you can come up with conjectures or guesses. Do they all eventually form lattices? That's a question. They appear to be bounded. They're only bounded because my students and I could not figure out how to get this to run for a long time. And this, if you do finitely many steps, is going to be bounded. So it's not that's just a problem of our coding skills. And what cases are dense? Great question. 0 pi over 3, 2 pi over 3 is another regular lattice. You want to run it at pi over 5. Yeah, I think my students tried that, and that was tricky. Jinx. If they look like lattices, do they keep doing that? If they look like total messes, do they maybe fill a dense set of points? Those are exactly the right questions to ask, right? So what are we seeing? And for those of you who don't know what dense means that if I were, say, to zoom into this, I got this, right? That's one attempt at zooming in to this construction. And then if it is actually dense, the problem with this is that we are using finitely many steps to describe an infinite process. So it's not gonna, these computational procedures are not gonna give us the whole picture, but they give us a sense of what to look for. This is why we use computers to do math, is to get to see the patterns and to make guesses about what's gonna happen. But eventually we have to write a proof. And that's what we do later. And so if you kept zooming into here, if you always find a cluster of points, then that's what we call dense. Versus what you're seeing here is that if I zoom in close enough, I'm going to have a lot of blank space, right? And that's what people are calling a lattice. This is a lattice. And these are examples of dense sets. And so the question is, when is this going to happen? I'm going to look at the can this be generalized to higher dimensions? Oh, good question. Yeah, so does each iteration grow polynomial or exponentially? Yeah, I think it grows like factorially. It's really bad. It's like it's combinatorial explosion is what you're getting when you're trying to put this in there. Okay. So I'll move on from here because we've asked lots of good questions. And so this is, this is a concept from point set topology that if you have a subset of a bigger set, we say that the subset is dense. And this is what I was describing before. If anytime you zoom in to elements in X, you still see elements of S. Okay, so zooming in, you still have a cluster of points. There's no way to get empty space. And our friends from before, Buhler, Butler, Launey, and Graham, actually showed that if you have a set of angles with more than 3 angles, you're going to get a dense set. And that's exactly what was going on here, is that here you have 3 angles and you get something nice. Any more than that, you're getting dense sets. Okay. And so this was proved by them in their paper. And Dmitry Nedrenko in a different paper said that if sort of the converse, if you have 3 angles, 2 angles is not enough. You don't get anything very interesting. With 3 angles, you always get a lattice. And with any more than 3 angles, you get a dense set. And so that's pretty cool that you can prove that and that you can do this, right? And so my students were actually wondering about something else. Something that you may have noticed or wondered about is that all of the angle sets I gave you had the angle 0 in it. Okay, so if you get any more than 4, even if you have 0, it's going to be dense. But here, it seems like 0 might be important. And so this is another project that my summer research students did. That's Yichen Liu in the left, and then Gabe Nelson in the middle, and Wu Yue Zhou, who made the origami from the beginning. They thought about this question. Assume that you have 3 angles, but they're all non-zero, right? So what does that look like? So that looks like, and still the seed points, every time our seed points are always going to be 0 and 1. Okay, so we have 0 and 1, and then we have 3 angles. Suppose that you have this angle, and this angle, wait, no, that's the same one. And this angle, right? So you have 3 different angles, none of them are 0. Well, one thing that you could say is, wow, that's not really a big deal. I can just rotate this whole picture so that, for example, this angle becomes the angle 0, and then everything rotates, right? So let's just rotate everything. And you rotate everything, but your seed point is still the seed point. So when you rotate everything, you move it as well. So what you're going from is, in this situation, you have 3 angles, none of which are 0. We have alpha, beta, gamma. We like using Greek letters for angles. And by we, I mean, it's sort of arbitrarily. Mathematicians decided this was a good idea. And the seed points are 0, 1. But then in this other situation, we have angles 0, sort of alpha prime, beta prime, let's call them something else. But then the seed points are 0 and whatever this thing is, and x, right? But then because of how the intersections worked, when we rotated everything, we rotated so that now one of these intersections is our sort of like new one. So in a sense, what we are thinking about is like, now we have 3 seed points, right? That might not be so clear, but the idea is you rotate the picture, but you get this extra point, right? That now you have to deal with. But if you could ignore this for a second, let's ignore this guy for a second, this point. What happens if you ignore it for a second? Then you get the exact same. So if you ignore this point, I'm going to circle it in blue, and blue means ignore for now. If you ignore that point, then you get the exact same situation, and you have 3 angles, one of which is 0, and by Nadrenko's result, you get a lattice, a very nicely organized set of points. And so how much can this thing mess up? So yeah, so then when we talk about lattices, they're these discrete sets. And so it's definitely not like both ever, right? You're not dense and a lattice. But in between could be like, maybe you had a lattice and now you get what we call a finer lattice, which is more dots, still evenly distributed, but you have more of them, right? Dense means that anything, right, a union of 2 lattices. That's a good question. And this is what my students tried to think about. And so let's just do the first sort of stage, where it is, here is the lattice that you would get if you ignore, again, here's the blue one. My students made this picture, and then I was never brave enough to redo it, but I wish they had made that point farther away from the other points. But this is the one we ignore. And so we do get the lattice. And so then the question is, what happens when we add this point in? And so what we do is we sort of zoom in. The nice thing about lattices is that you have this thing called a fundamental parallelogram. So if you look at this, I'm going to actually do this in a different color. My apologies to the colorblind folks out there. I hope that this is different enough. Is if you look at this little parallelogram, you can see that this is repeated, this pattern, whatever is happening there is going to be repeated everywhere, okay? And so if we understand what happens in this little parallelogram, we understand everything. So we, let's keep that. I'm gonna move on. And so now I'm gonna draw a picture freehand, and that's gonna be, this is the most dangerous part of my talk, is that this is never goes well. So let me draw that parallelogram. And then here's the point. And then the 3 angles that we had were this one, and 0, right? And so this is the picture zoomed in. Now, what can I do? I can draw any of those angles through any of these points. So for example, I can draw a horizontal line through this sort of what was originally our seed point, right? This intersects over here. And so now I can draw this line over here, which intersects here. And I can repeat this process. Whoops, no. And then I get something else over here, okay? And then what happens there is that I can repeat this process again. And so what you're getting are smaller and smaller versions of this rectangle. And so how are we gonna know if this is dense or not? We're gonna know, so this is the good picture for it. We're gonna know if this is dense or not. It has to do with sort of basically how divisible is this length by these lengths, right? And so what my students found was like some really cute generalization of the Euclidean algorithm, where you can think about like the Euclidean algorithm, but for real numbers. And so if you get that this process basically is an iterative process. So you're going back and forth, and that has to terminate. And it's only going to terminate if things are sort of certain ratios are rational. If those ratios are irrational, then you get a dense set. So it's really, really cool. I can't go into all of the details right now, but you can see how messy this can get by just adding that one extra point or by having that non-zero angle. And in fact, the theorem that we came up with, it actually had been found by someone else, so we never published this anywhere, but I thought it was cute and I wanted to share it. It really has to do with, you know, what can I say about those angles? And if this ratio is rational, then we get a lattice. It might be much finer than the first lattice we got from that rotation. And then the upshot is when it's not rational, then the set is dense. And this comes down to like this sort of Euclidean algorithm or generalized Euclidean algorithm and the law of sines, which I had not used in my whole life since I learned it. And then it sort of came up here. So that was really fun. Anyway, and so we got a theorem. And so now we've pretty much done everything we could do in 2 dimensions. So my students and I came up with this idea to, well, one of them was my thesis student and the other one had been my student and then became a professor at Bates College. And so now it's sort of like a sort of vertical integration of collaborations. Deveena is now after this, she decided she wanted to go and to do a PhD in molecular biology and biochemistry. So I don't know how, whether this experience threw her into biology or she just found her calling in a different way, but we're still working together. And we decided to say, well, what happens if we generalize this to higher dimensions? The problem with generalizing to higher dimensions is that how do you do this, right? This is a question that I was getting. I've been working on this project for a while. And when I was talking about what I did with those summer research students, people would be like, well, have you tried this in higher dimensions? And I was like, I don't even know where to start. But working with Sara and Deveena, we decided that we could keep 2 seed points, 0 and 1, but now we have to sort of contextualize this as, I mean, we're not in complex numbers anymore, but we can sort of pretend that we are in 3D. In 3D, we don't have multiplication anymore, but we can still sort of call things 0 and 1 when I mean 0, 0, 0 and 1, 0, 0. And then we can have angles that basically, this is sort of 90 degrees in one direction. and this is the 45 degrees in another in the same direction. And then this is 90 and 45, but in a different plane. Okay, so what that looks like is like this. And so then you can start playing the same game where you draw a line through a point, and you just drawing a line through point 0 with angle, like say, let's say 0 and angle I, that's this line. Just think of it as like the line that goes through those 2 points, right? And so there's no problem with thinking of those directions. It just says these are the directions in which we want to go. There are sort of mathier ways to explain this, but you can play this game again. And so you draw lines through points, and then you find new intersection points, and you throw those into your set, and you see how far you can go. And what you get from this construction, I don't know if you noticed, I hope you did, that this is basically what we did for the Gaussian integers, but then we added another plane for reference. And so what you get is some sort of like 3D Gaussian integers. I can't call them that really because there's no multiplication doesn't make sense anymore. We'll see another example where it does. But we can have something like z plus zi plus zj, which I just mean combinations of the form a plus bi plus cj, where a, b, and c are integers. And so you can just do that forever. And we get a lattice. Again, you have a generalization of a lattice into n dimensions. I'm trying to make sure that I don't use too much jargon here, but you can always find this sort of nice grids in n dimensions, okay, where you just only do, you have some generating points, and then you get all of the combinations, integer combinations of those points. And so, and this is what we proved, Sara and Deveena and I, for n dimensions. We proved that if you choose your angles carefully enough, you get any lattice that I give you, as long as we contain the point 1, okay? And so a lattice containing the number 1. So anything that looks like, oh, well, I can just write it down. Anything that looks like z plus z, you know, tau 1 plus z tau 2 plus z tau n minus 1, because there's n dimensions, okay? So that was super cool. And you just have to be, you know, clever and pick the right points and make sure that you get the right intersections in there. And then we proved a few more things on lattices. We showed that if you get a lattice, then you had to have at least 2n minus 1 angles. And I don't know if you noticed that pattern, but for like 2 dimensions, for lattice, we needed 0, alpha, beta. Oh, and now we always have the angle 0, because as you saw in 2 dimensions, it was a mess. If we were going to generalize, we tried to generalize the case where we always have 0. And then for 3D, we had, for the example, we had 1, I minus 1, sorry, j minus 1. So there were 3 here, there were 5 here. So every time you get 2n minus 1 angles, okay? And you have to have at least that many. One thing we don't know is that if you can always find a generating set of angles that has exactly 2n minus 1. We still can't prove that. Butler, Buhler, Launey, and Graham's result still is useful, because if you can find 4 angles that share a plane, a 2-dimensional plane, then that already is dense. And so you have no hope of your thing being a lattice, right? And so that helps us. And then you might ask, like, well, what happens if I have a lattice and I add another angle? See, in 2 dimensions, it was easy. If you had 3 angles, you had a lattice. If you add another angle, then you know it's dense. It is not that simple, because now, so instead of having always an intersection, you could have sort of lines in 3 dimensions that just live in completely different planes and just never intersect, right? Or, well, they intersect, but in weird. Anyway, so you could get a finer lattice, so more dots on the grid if you add another angle. You could get a dense set, which is what we expect in the 2-dimensional case. Or you actually could add an angle that changes nothing. You could add irrelevant angles, which you don't have that freedom in 2 dimensions, but in 3 dimensions, you could have 2 lines that are like parallel like this, right? And so, so I want to show you those 3 examples now. And so I'm going to show you one where you get a finer, well, I'm not going to show you all of them. I'm going to show you an example where you get a finer lattice, and I'm going to show you an example where you get a dense set. This one is more complicated. Okay, and so suppose you're in 3D space. This is the example that we just saw. We just saw this. You actually can add an angle that creates this new intersection point that is closer to 0 than all the ones that you started with. And what happens there is very similar to what we saw with that example where you didn't have 0, which is now you can create a sequence of points by just doing this sort of repeated thing that approaches 0. Okay, but it's never, it's an infinite sequence of like thirds and thirds and thirds. And so what you get is that you have points that are arbitrarily close to 0. And so, and that all sort of propagates. Everything gets copied again because you can do all of the same things for every point. And so then you get a dense set. And then what we really should be thinking about, because in 3 dimensions, like I said, that's not really the generalization. It doesn't generalize all the things that we would want to generalize about complex numbers. And this is exactly how Hamilton came up with the Quaternions, is that he really wanted a generalization for Gaussian integers. And in fact, he got the idea while walking across a bridge. And now there's a memorial plaque in Broom Bridge in Dublin that says this. So you can go look at this when you are in Dublin. And this was all you needed to have a multiplication that made sense in higher dimensions. And so you can start, look, I'm not doing anything very fancy. I'm just doing the same thing, but adding another dimension. And you get exactly the generalization of the Gaussian integers. This is called the Hurwitz order, for those of you in the know. And then you get, if you add a different set of angles. So in this case, we had these 4, and in this case, you have a different set, and you get a finer lattice, okay? And so somehow you're not getting the exact same thing, even though you're only changing things by a little bit. So there's a lot more to this story, and this got really mathy really fast. But there's another side to this story, which has to do with the Quaternions and the fact that you have multiplication. And when I say origami rings, I don't mean this, even though they're cute. I mean is, can we multiply? So yes, for the Quaternions, it doesn't matter if the set is dense or not. So it's a totally different question. And Buhler completely understood this in 2D. And we don't really know how to go about this in higher dimensions, except, you know, Quaternions already have all these properties. And so that's it for me. That's another Robert Lang art piece. And yeah, thank you so much. And if you want to read about this, our paper just came out on the archive today. So you can go look if you want to know more about like the mathy parts. Thank you.
Thank you very much, Adriana. That was very fascinating, very cool talk. And we have had a few questions go by, I believe, a few comments. How about the octonions?
Oh, yeah, totally. We can do that. Yes. We can do that in all dimensions, right? And so then we can generate octonions, like that's just, 8-dimensional space. But yeah, so one of, if you really, these words will make sense to some of you. What Sara really wants to do is do this for central simple algebras, which is sort of where you get this this nice structure, and that's an algebraic structure. Yeah, so I already mentioned about the 4D Gaussian integers. So you can generalize this in many, many different ways. I invite you to pick your favorite generalization, because we said, okay, let's just keep lines and points, but there's so much room to create there that, yeah, just pick your favorite generalization. If you want, like, prescribed planes, or like only use like anything of dimension like n-1 and only use those in those intersections, sure. Like I don't know what you could get. So yeah, there's so many ways to generalize this. I'm sorry, I don't know how to fold paper in higher dimensions.
Well,
I apologize.
That's what we all want.
I know.
4-dimensional paper.
4-dimensional paper. Sorry, but this is so new. This is why I love working on this with students, because all of the questions are open. And for example, with Deveena, we started playing with whether we could do this in hyperbolic space. And and like lines are now these like semicircles. And so what happens when you intersect them? Can you still create we got super stuck, so we went to higher dimensions. But again, like that's an open idea. So anyone who wants to pick it up and work on it, do it, and then tell me about it, because I want to know.
That sounds really cool.
Is there a theory of folding 3-dimensional space? I know it would have to be in a higher dimension.
Right. And so that's the other thing that we miss, is that we're not thinking about like the folding. We're basically like folding and then unfolding, right? And so we never use that extra dimension that you use to make a fold. So that there's all this other stuff that you could do, like, how people prove that you can trisect an angle using origami. And that's because you get all their new axioms from like allowing folding. And so then you can get like a trisect an angle. Look that up. It's really fun.
Do you know if the dense constructions necessarily generate free groups?
Yeah, I think it is always free or like finitely generated, at least in 2 dimensions. So the Buhler paper is really cool, because like he basically comes up with these generators for the ring. And he can tell you exactly what conditions you need to be sure that it's a ring or not. And it is sort of a finitely generated thing. So it's dense or not. It's sort of independent. But I have no idea how this works in higher dimensions, the ring stuff.
Okay. Well, thank you once again, Adriana.
Thank you.